Okay, everybody, section 1.2 really isn't too bad. It's not as long and it's not as random and rambling as section 1.1 was. Here we're just a little bit more focused and figured it'd be a good idea at the beginning of the year to go back and talk about two big ideas you've been dealing with since Algebra 1, those being linear and quadratic functions. And the nice thing about this is you've been using these types of functions almost nonstop since you learned them, 4 years ago. So I think most of this you're probably going to remember pretty well. So not too bad of a section. All right, so we start off talking about a linear function, and as the word linear implies, we're talking about something that is a line. But our real formal definition, in a way that's maybe a little bit more applicable to the way we're going to be talking about functions later on this year, is that a linear function is one that has a constant rate of change. It always increases or decreases at the same rate, regardless of where it is that you're measuring along that function. And the word we're going to be using a lot this year for rate of change is one that you know well. That's the concept of slope. So the equivalency between the words slope and the phrase rate of change, that's pretty darn important. We're going to be using those two a lot together this year. So that's something we better start associating here mentally. Slope is our rate of change. And as we're talking about a linear function, and obviously I didn't draw one very carefully, what I think we all know is that we've got an infinite number of points that are located along a line, but I went ahead and just highlighted 3, and that would be A and B and C. And of course the idea right here is that if we were going to go from point A to point B, we would move vertically a certain amount. Of course, we call that our rise. And then we would move horizontally a certain amount. That would be called our run. And whatever that ratio of rise to run is, becomes the slope of that particular line there. So we could measure the slope from A to B, and whatever that number ended up being, we would write it over here. And then if we did the exact same thing going from B to C, we would have a rise here, and we would have a run going right over here. Now, if I did what I was hoping to do here, which was to make B the exact midpoint between A and C, what we would find is that this rise over here and this rise here would be identical. Likewise, the runs from A to B and B to C would be identical as well. But the cool thing is, even if I messed up and I didn't put B directly in the middle, in which case those tick marks would no longer apply because we're not congruent here, the important thing is that the ratios of rise and run would be exactly the same once you simplify those fractions. So the slope of line segment AB would be the same as the slope of line segment BC. Those two slopes would have to be equal to each other in order for this to be a linear function. And furthermore, going a little bit different direction here, if we wanted to take a bigger step, if we were literally going to go from A to C all at once, your rise now is bigger than it would have been before, but then again, so is your run. So then we can see here that the slope measured from A to C is still going to be equal to the slope from A to B and the slope from B to C. No matter where you are on a linear function, no matter which 2 points you choose, no matter how close together they are nor how far apart they are, those slopes are always going to be the same. And that's one that people tend to remember pretty well, so I don't think we need to beat that horse until it's that dead. Anyway, back to this one right here. Forms of linear equations. There's 3 of them that we probably ought to know. Slope-intercept form is the one that you guys learned very, very well in algebra, and you've used a lot since. That, of course, is y is equal to mx plus b. And every time this year we write down a formula, everybody, we're at least going to talk about what the variables represent. Again, most people remember this one just fine. M is representing slope for a reason that nobody seems to know or understand why we use that variable, but we always do. B is our y-intercept for a reason that I'll explain in just a moment. And then this kind of eludes people once in a while. The other 2 variables that are in this formula here are ones that we don't normally substitute values in for, and that would be the x and the y. What I mean by that is that we're used to seeing an equation maybe of the form y equals 2x plus 5, and we can look at that pretty quickly and realize that our slope is 2 and that our y-intercept is 5. But when I ask people what the x and the y represent represent, even good students, even at this level, sometimes scratch their head and don't quite have an answer. And the key to that is something that should be emphasized a little bit more strongly at every level of math you guys have ever taken. It doesn't matter what it is that you're graphing, whether it's a line, a parabola, a cosine wave, an exponential growth function, a hyperbola, anything that we are graphing, the x and the y within that formula here represent the coordinates of any ordered pair that's located on that graph. And even the way that I'm explaining it right there is maybe a little bit backwards. The reason a graph has the shape that it does is because that is the arrangement naturally occurring of all of the x and y coordinates that satisfy that. So if we were to think about a point that might be located on the line 2x plus 5, you guys could give me any x coordinate you wanted, but let's go with maybe 3. The y coordinate going along with that would be 2 times 3, which is 6, plus 5 is 11. And now working backwards, we could substitute those values in. 11 would equal 2 times 3 plus 5, and not surprisingly, because we concocted the point this way, we end up with a true statement of 11 equals 11. And that just verifies here that the point 311 is one of the infinitely many solutions to this two-variable equation. Okay, we probably didn't need to talk about that as much as we did, but always important to know what your x and y actually represent. Now, the second form we're going to talk about is point-slope form. And in my experience, this is one that is not emphasized as strongly as it should be at every level of math up until this point. We are going to use point-slope form a ton this year, everybody. So if you've been avoiding it for the last 3 or 4 years, it's time to put on your big kid pants and realize that it's not all that scary. First things first, when do we use point-slope form? The name tells you the answer to that. You use point-slope form when you know a point that's located on the line and you know its slope, as opposed to slope-intercept form, which you use when you know the slope of a line and you know its y-intercept. M is your slope, B is your y-intercept. But back to point-slope form here. All right, let's see if we can understand where this formula comes from. So the formula for point-slope is going to be y minus y sub 1 is equal to, here's M, your slope, times the binomial quantity of x minus x sub 1. And that's the formula for point slope. Now that's what you guys really need to know. I'm going to muck this up just a little bit trying to explain a few things in just a second, but here we go. One thing people never seem to understand is where that formula comes from, and it's not witchcraft and sorcery, guys. It actually makes a lot of sense. If we were to take the x and the y and put a subscript of 2 in each one of them, which we certainly can do. All right, we can do that. And now, if we wanted to solve this equation for m, we would divide both sides by the quantity x sub 2 minus x sub 1. And if we do that, and I wish I had a little more space right here. All right, that looks like that. These cancel, and you just get m equals, and what I'm hoping you guys recognize right here is the quotient. It's called a difference quotient, the formula for slope of a line, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So it's really just a reworking of the formula for slope, which most people at this level are able to recall without any great difficulty. Now, this is one that I do actually want to label, though, when we're talking about point-slope form as to what everything stands for. Not surprisingly, m is still representing the slope of our line. But what happens here, guys, is that if you take x1 and put it together with y1, that there represents a point on the line. And it doesn't have to be a specific point the way that it did back here in slope-intercept form. The b wasn't a random point. It had to be very specifically the y-intercept. But in point-slope form, you don't need to be that specific. You can use any point that's located on the line. As long as you know a point and the slope of the line, you can write it in point-slope form. And that right there is probably worth pausing for just a second and talking about this. When we think about the uniqueness of a line, and it makes no difference what line I draw right here, everybody, but if I were to just draw something that kind of, let's draw a decreasing line that maybe looks like this. Ask yourself these questions right here. How many slopes does a line have? Well, the answer to that is just one. How many y-intercepts does a line have? The answer to that is just one as well. So because both slope and y-intercept are unique numbers in each particular line, there is one and only one slope-intercept form of every line that exists. However, if we think about point-slope form right here, you would ask yourself these questions. How many points does a line pass through? And of course, the answer to that is that there are infinitely many points that a line passes through. How many slopes does a line have? Well, just one. But the fact that we've got infinitely many points means that, you guessed it, there's an infinite number of ways that you could write point-slope form of the same line. So, you might be doing a homework problem one way, a friend might be doing it the other way, and you guys might have two different answers for the point-slope form. But if we were to take both of our point-slope forms, which look different, and convert them both into slope-intercept form, we would all end up at the exact same spot. So that's worth noting as well. As I said earlier, we're going to use point-slope form a ton this year because in a lot of the tangent line problems that are kind of bread and butter concepts here in first semester Calc, we are going to know our point of tangency and the slope of our tangent. So with point and slope in mind, we're usually going to go to point-slope form first and then sometimes convert that into slope-intercept form. Okay, guys, the third and final form of a linear equation, let me be honest with you, is really worthless and you will never see me use it during the entire year. But occasionally it shows up in the way that they write a problem, so I just want you guys to get a little refresher on this one. Standard form is written this way. It's a times x plus b times y is equal to c. Okay, and just a couple of important notes right there. Once again, the x and the y still just represent any ordered pair that's located on that line. But in this case right here, the a and the b and the c don't really represent anything unique on their own. Notice these are capital A's and b's and c's, which makes them a little bit different than this lowercase that we were using right over here. Basically, guys, if you want to get an equation that's in standard form, you'd probably start by writing it in slope-intercept form, and then just follow a couple of simple rules of algebra to try to get it into standard form. So the first rule right there is the order, and you can see that already from the way that it's written. Standard form is unique in that it has both the x term and the y term on the left side of the equation, and then the constant is over here on the right all by itself. A second rule for standard form, we are not allowed to use any fractions or decimals here. So what we would say here is that a, b, and c must all be integers. So what do? Well, if you ended up with something like a 2/5 from slope-intercept form, you would go ahead and multiply every term in that equation by 5, or whatever the least common multiple of all of your denominators is, to get something to work out completely in terms of integers, no fractions or decimals. And finally here, actually two more things. One more, a has to be positive, everybody. If for some reason a ended up being negative here, we would multiply through by -1 and make sure that that first term is positive. And the last one is difficult to write or put into words, so I'll just talk about this real quickly. The values of a, b, and c cannot have a common factor other than 1. There's a phrase I learned for this in a college class. Those three numbers must be relatively prime. Let me show you what I mean. If you were doing all this work right here to get rid of fractions, and you ended up with something like 3x minus 12y is equal to 9. This equation is technically not in standard form. Now, it does meet the first three criteria. The order is right, with x and y on the left and the constant on the right. A, B, and C are all integers, and A is positive. But I think you guys can look at this pretty quickly and see the problem. There's a common factor of 3 here. So all you would need to do now is just divide each term in the equation by 3, and that would now get you to an x minus a 4y equals 3, and that equation is in standard form. As I said, guys, standard form really isn't good for very much. I could teach you some things about it to graph out of standard form, but it's basically the shortcuts you would learn anyway by taking standard form and converting it back into slope-intercept where you solve for y. Like, for example, and I'm winging this, guys, because I don't have these memorized, the slope of a line in standard form, I'm pretty sure, is the opposite of a divided by b, and the y-intercept of a line in standard form, I believe, is c divided by b, but frankly, those rules are more trouble than they're worth, and you shouldn't waste your time trying to memorize them. You'll figure that out fine on your own. Okay, so that's a little talk. We use slope-intercept form a bunch, we use point-intercept a lot, and we really don't use standard form very much at all. Okay, that's as much as we were going to do with linear functions, guys, because I think you know this all pretty well. Let's move on now to quadratic functions. And, again, stuff that you guys probably know pretty well here. A quadratic function is a function that can be written in either of these two forms here. The first one, f of x equals ax squared plus bx plus c, is what some authors are going to call standard form of a quadratic function. Some of them are going to call it expanded form. Now, by itself, I'm not sure if the phrase expanded form means anything to you until you look at it in contrast to what's over here on the right. And the second form over here on the right, f of x equals a times the quantity x minus h squared plus k, you guys learned, I believe back in Algebra 2, as something called vertex form. But another way to look at it here, the opposite of expanded form, would be something that is in factored form. And the key to both of these is the fact that we have a binomial quantity that's in parentheses here. And that's different from standard or expanded, where everything is multiplied out and there are no parentheses. Now, both of them work just fine, and I think you guys probably know that. So here, in terms of the most obvious things we're going to talk about in a while, a quadratic function is going to give us a parabola, which consists of a vertex located right about here, and then that quadratic function can either open upwards or downwards, and with varying degrees of width or girth to them is the word I like to use for that one. So a normal upwards opening parabola might look something like this. Okay, one thing worth pointing out, when we talk here about vertex form, here are the two magic letters that showed up a lot over the last couple years. H and K, when you put them together, make up the ordered pair that is your vertex. So I guess while I'm drawing things, everybody, I'll put a dot right there and say that that is the ordered pair of H, comma, K. Now remember here that the k very often used to be over here on the left, and we would write this left side as y minus k. But now they've left f of x over here on the left and brought the k to the right. So that actually means that h is normally the opposite of how it appears. What I mean by that, guys, is that if this is like x minus 5, h is actually positive 5. Okay, but k is now straightforward. If k is a minus 5, then this k is a negative 5 as well. Okay, a couple of other things here. Every quadratic function is symmetric with respect to its axis of symmetry, which is really a stupid thing to say when you think about it. Yes, it's symmetric with respect to its line of symmetry. But anyway, that vertical line there, because it's vertical, is going to be of the equation or the form x equals, and then the x-intercept of this line right over here is exactly the same as the x-coordinate of your vertex. So x equals h is what we would consider then to be our axis of symmetry. The value of a here is going to determine how wide or how skinny that parabola is. And that is also true in standard form right over here. And the sine of a is, of course, going to determine which direction this thing opens, whether it's up or whether it's down. All right, so that was one we were going to talk about pretty quickly. I think you guys probably have that down, so let's move on. And I want to talk quickly here, guys, about the 3 ways of solving quadratic equations. So, if we were in class, I would ask this one out loud. The first way, and by far the best way, when it's possible to solve quadratics, is the method of factoring. Now, I should be clear here before we move on at all. Factoring is definitely the best way to solve quadratics. It's the easiest and the most efficient, but the problem is it doesn't always work. But You guys have gotten good enough, I'm thinking, at factoring over the last 4 or 5 years that you're going to kind of recognize certain patterns in numbers, and this one would be an example. So x squared is equal to 11x minus 28, and we might look at the numbers 11 and 28 and already be thinking about numbers that add up to 11 but then multiply to 28. So the first step to solving by factoring is to set this equation equal to 0. We're going to use something in a moment called the zero product property, and it only works if we can get one side of the equation equal to 0. So this is an x squared minus 11x and a plus 28 is now equal to 0. And we would always try to think about this. We're looking for two numbers now who multiply to positive 28 and add up to a negative 11. All right, so I set up my blank factoring right here, and here we go. Two numbers that are going to multiply to x squared are going to be x and x. If you remember how to do this from back in the day here reading signs, the fact that c is positive tells me that these two signs here, there and there, are going to be the same. The fact that b is negative tells me that these are both going to be minus. Okay, so minus and minus. And again, looking for two numbers now that multiply to 28, and because the signs are the same, we need them to add up to 11. That's going to be a 4 and a 7. Now, back to what I said just a moment ago. This next step is so ingrained in your thinking that you guys just plow through it and never really give it much thought. But what we are using right now, everybody, is something called the zero product property. And the zero product property says that A multiplied by B can equal 0 if either one of these two factors is equal to 0. So that will happen if A equals 0 or if B equals 0. Well, guys, here's our A and here's our B. So we're going to dive into that in just a second. But let me be clear on something here. Let's go back and talk about what I just wrote there in red. A times B will equal 0 if, really and only if, either A is 0 or B is 0 or both. Now I want you guys to think about that for a second. That's not true for any other number. If I were to put a nice clean composite number there like 12, A times B equals 12 has an infinite number of solutions to it, but I don't know anything about either one of those two numbers. A might be 12 if B were 1, but it doesn't have to be 12 because I could have picked 4 and 3, or 6 and 2, or 24 and 1/2, or 120 and 0.1. There's an infinite number of ways that can work. I don't even know the sign of my solutions. A could be positive if B were positive as well, but then again, A could be negative if B were a negative number. So there's actually a lot that we know here by dealing with 0 here. The only way that A times B can equal 0 is if one of those two numbers, or one of those two factors, I should say, is equal to 0 on its own. It's impossible to take two non-zero numbers, multiply them together, and get 0 for a result. So this property only works, you guys, when we have a 0 over here on this side. I see people try to apply this property with other numbers over there on the right, and it simply does not work. All right, from here, you guys usually skip this step, but this works if either x minus 4 equals 0 or if x minus 7 is equal to 0. And now we just solve each equation, and we get x equals 4 or x equals 7. And those, everybody, are our two solutions. Now we're going to verify those in just a second, but before I do, I want to take a moment and talk about this little word right here and talk about how even for smart people like yourselves who are now in AP Calculus, this can be an incredibly confusing word. So here's what I want to say nice and clear, guys. The answer to this question is x equals 4 or x equals 7. But the tricky thing about that is when you say the word or kind of in an English context and you're thinking about that, it makes it sound like you only need one of the two answers. Hey, you got it right if you got x equals 4, or you got it right if you got x equals 7. So to get the answer fully correct, we really need to include both of those two solutions. And a lot of people then think, now this is wrong, so don't do this in your notes, a lot of people think then that since I need both of them, or isn't the right word, and I really should put the word and. Now let me tell you that I understand what you're thinking. The correct solution is x equals 4 and x equals 7. You need to have both. However, this says something mathematically that I don't think you guys think that it says. You're telling me with this answer right here that a value for x will satisfy the original equation right over here if that value of x is 4 and it is 7 at the same time. And of course, there is no number out there that's equal to 4 and equal to 7 simultaneously. Now, what we really mean to say right here, guys, is that a value of x will satisfy this original equation if that value is equal to 4 or if that value is equal to 7. It can't be both simultaneously. So that's where there's a little bit of a difference between the mathematical definition of the word or and then the English definition of the word or. You guys are usually more inclined to use the word and here, but unfortunately that's mathematically incorrect. The spot where that does become important, guys, is if we were dealing with inequalities. Like if I said, give me a value of x that is greater than 5 and x also needs to be less than 10. Now, if that's what we were looking for, think of some numbers that satisfy both of those. 6 would work, 7, 8, 9, 9.8, there you go. That's the significance of and. But if I now change this to an or, think about that for a minute. Give me a value of x that is either greater than 5 or less than 10. I'm sure you could think of one, but can you think of one that's not greater than 5 or less than 10? And the answer to that is no, you can't. Every single real number that exists is either greater than 5 or less than 10. But not every single real number that exists is greater than 5 and less than 10. So like I said, mathematical difference right there. I said we were going to check these, but I think we got it pretty quick. X is 4, so that's a 16 on the left. And then 11 times 4 is 44, and 44 minus 28 is 16. So check, 4 works. And let's do a 7 now. 7 squared is 49. And over here on the right side, 11 times 7 is 77, and 77 minus 28 is 49. That one works out as well. Okay, so nothing difficult with factoring. You've been doing it a lot over the last several years. The second method is one that I feel doesn't get the respect that it deserves from snot-nosed punks like yourself here, because you don't like it, and it doesn't always work, I'll grant you that, but when it does work, it is, as we used to say back in the day here, everybody, the bomb diggity. And that method right here is completing the square. And if we were in class right now, I would expect to hear some groans and see some eye rolls and say, oh my God, they tried to make me learn this 2 years ago and I just didn't do it. Okay, fine, be that way. All right, stand in the way of progress and enlightenment. Completing the square works really, really well though. Better than the third method we're going to talk about in a second, under certain circumstances. So first of all, let's talk about when completing the square works. Actually, I should be clear. Completing the square will always work in every case. It'll get you rational solutions. It'll get you irrational solutions, and it'll get you imaginary solutions. Okay, those are the three big ones. Factoring, which we talked about just a second ago, really only gets you rational solutions, like x equals 4 or x equals 7, or even if it was something that was a fraction, like x equals 3/11ths, yeah, factoring would get you that solution as well. Now, completing the square works all of the time, but you really only want to do it when two things happen. Number one, we only really want to do completing the square when a is equal to 1. Which in this case, hey, what a coincidence, it is. The other thing you want to check for is that we want b to be an even number, which again, by dumb luck, b is negative 12 here, and it is. If those things were not the case, you absolutely could do completing the square. It just gets more difficult, and at that point, it's probably more trouble than it's worth. So let's talk about the phrase. Now really, what gets omitted from the title right here is this really should be completing the, and there's a couple words that we left out here. We really are completing the perfect, ooh, that was tough, the perfect square trinomial. So really that phrase of 3 words right there should really all go together. We're completing the perfect square trinomial because when you have a perfect square trinomial, it factors very nicely in a way that's pretty easy to solve. Well, right now, everybody, what we are dealing with on this left-hand side is not a perfect square trinomial. It's been a long time since you talked about this, so let's do the checklist for that. Is the first term a perfect square? Yes, it is. Is the third term a perfect square? No, it's not. So actually, I'm going to stop right there. I won't even tell you the third test. We'll get to that in just a minute. So the first step to completing the perfect square trinomial, and this is unlike the other two methods, we want to bring this constant away from the left side and onto the right. So that's going to be an x squared minus a 12x. Now you want to leave yourself some room and bring your c value over there to become a negative 4. Now, to make this left side a perfect square trinomial, we're obviously missing something right here. So, how do we make it a perfect square trinomial? Well, here's a method you've probably talked about in the past but maybe forgotten. This works anytime that a is equal to 1. What you're now going to do is take your b value, which in this case is negative 12, cut it in half, and square that value. So as we look at b, which is negative 12, we cut that in half to get a negative 6. We square that negative 6 to get a positive 36, and we're going to add that 36 here on the left side. And what we've just done, everybody, is created a perfect square trinomial over here on the left-hand side. And of course, I can't just add a 36 on the left-hand side because I feel like it. I also have to balance that out by adding the same value over here on the right. Now let's talk one more time about why what we just created, that I'm going to put brackets around right now, is a perfect square trinomial. 3 tests. First, the first term, x squared, is a perfect square. Check. Second of all, the last term, positive 36, is a perfect square. Check. And the third one is a pain. You couldn't write this out even if you wanted to, so you just got to use the force and feel it here, everybody. Here's what you're going to do. You're going to take the square root of the first term, which is x. You're going to take the square root of the last term, which is 6, and if you multiply those two together and multiply then by 2, that needs to get you this middle term right here. And sure enough, x times 6 times 2 is 12x, and that's what we got there. So those are the 3 things that have to work out in order for a trinomial to be a perfect square trinomial. Now, the whole point in doing this, everybody, is that this is now becoming a factoring problem, just like the one that we did a few moments ago. We are now going to be able to factor the left-hand side. But this is another thing that some of you guys have been resistant to over the last couple of years. When I see somebody now start to factor the left side by drawing this, I already know they've missed the point right here and they don't get the joke. Yeah, you could factor the left side this way, but the whole point in creating a perfect square trinomial is that this now factors into a single binomial squared. And that's incredibly important to understand. Okay, how do we factor this thing? Well, we kind of talked about it already. You take the square root of the first term, that goes right here. You take the square root of the last term, that goes here, and then be careful now, whatever the sign of b is, that sign goes right here. So if that was a plus 12x, this would have been an x plus 6. All right, but this is the fast and efficient way to factor a perfect square trinomial. We clean up the right side. Negative 4 plus 36, last I checked, was 32. And now, the beauty of what we just did here is that we just took an equation, or I really should say an expression just on the left side that had both an x squared and an x, and we now found a way to write it right here with only one x in it. And the significance of that, everybody, is that with just one x, we can now use inverse operations to solve this equation relatively efficiently. We have to get rid of the square, so we'll do the square root of the left and the square root of the right. That is going to give us an x minus 6 equals. Now, 32 is not a perfect square, everybody, but hopefully we remember this one. That factors into 16 times 2, so that's going to become 4 times the square root of 2. And be careful here. Anytime you take a square root of a positive number, there's actually 2 results, positive or negative for root 2. And the last thing we need to do now is to add 6 on both sides. So we're going to write this as x equals, and normally, guys, as a matter of convention, we like to put that number, that 6, in front of the plus or minus part right here. So that's 6 plus or minus 4 times the square root of 2. You could write that as x equals plus or minus 4 root 2 plus 6, but I don't want you guys to get laughed at when you go to college. This is the way the cool kids do it, all right? So that, everybody, is our solution. And I do want you to note that just like in the last problem, we do actually have 2 solutions to this quadratic. The plus or minus right there means we could have either one of those cases there. This one is more difficult to confirm by plugging back in, so I'm going to ask you guys to trust me on that one, but that's how completing the square or completing the perfect square trinomial works. Again, make yourself give it a shot once in a while when these 2 conditions here are met, when A is 1 and when B is even. Frankly, it's not that bad when B is odd. Like, for example, if this was a 5 right here, when you go to cut it in half, you just think of it as a fraction. Half of 5 is 5 over 2, and then when you square 5 over 2, you get 25 over 4, and that would have to go here and here. It's not a ton of fun, but it's not that bad. Do it once in a while, okay? It's like running a marathon, you know. Don't do it often, but, just once in a while. I'm just kidding. Mr. Fontana hates running. Okay, so that's completing the square. And the third and final method is the one that you guys probably would have chosen second right here, and that is going to be the quadratic formula. Now, before we go too much further here, guys, benefit to the quadratic formula, it always works. Always, always, always. It'll get you every kind of solution you could come up with to a quadratic equation. The downside to it is that it's a little messy and it takes a while. And if there are other methods available to you, for example, if it's one that factors, or if it's one that meets these conditions right here to work well for completing the square, those methods are going to be much faster than using the quadratic formula. But as it is, let's dive into it. Now, I'm sure we all remember this. Some of you probably have it tattooed somewhere on your body because it's just that important to you. But the quadratic formula, everybody, is x is equal to, and it is a big old fraction. Up in the numerator, it is the opposite of b plus or minus the square root of b squared minus 4ac all over 2a. While we're on that subject there, let's talk about this for just a second. This quantity right here that I'm going to underline, underneath the radical, or what we might call our radicand, b squared minus 4ac is what's called the discriminant in the quadratic formula here. And the value of the discriminant is important. Let me show you what we can do with that. I'm going to switch to green here for just a second. If we were to try to figure out our discriminant, let's see what's going on here. B squared. Well, b is 9, actually negative 9, and if we square that, we get 81. So that's b squared minus 4 times an a value of 2 times a c value of 5. Let's see, the 2 times 5 is 10, times 4 is 20, 81 minus 20 is 61. So what in the world have we learned by now knowing that our discriminant is 61? Well, ask yourself the question, what are you going to do with that discriminant if we do end up doing the quadratic formula? Well, that discriminant is your radicand. We're going to be taking the square root of 61. So there's 2 things to glean from that. First question. Is the square root of 61 real or imaginary? The answer to that is that it's real because 61 is a positive number. Now, if our discriminant were negative and you went to take the square root of a negative 61, that tells you your solutions would be imaginary. So we know they're real. Next question. Is 61 a perfect square? When you go to take the square root of 61, are you going to get a nice result? And the answer to that is no. The square root of 61 is real, but it's irrational. So that tells us already, guys, that for the 2 solutions we're looking for, we're expecting real numbers, but they're both going to end up being irrational, kind of like they were back here in example B with a square root involved. Example A would be an example of 2 solutions that were both real and rational. Okay, so that's the discriminant. I'm not going to erase that because that actually saves me some work as I get into the formula here. So quadratic formula, x equals big old fraction, and up on the top we begin with the opposite of b, which is going to be positive 9. Plus or minus the square root of, well, all that work of the radicand we've already done, and that's going to be 61. And now I realize I didn't need to make that fraction bar so big, sorry. And then down on the bottom, 2 times a, well, a is 2, so 2a is going to be a 4 down there. And now, these problems can get very, very different in terms of the amount of work that you have to do at this point. What we would try to do is simplify the radical, if that was at all possible, and then see if we can cancel out any identical factors from both the top and the bottom. The really good news I have for you guys at this point is that 61 is a prime number, which means the square root of 61 cannot be simplified and nothing can be combined here. So actually, guys, it's ugly, but that is as good as this answer is ever going to get. Let me just give you a quick hypothetical of when you might have to do more work. What if you ended up with something like x is equal to an 8 plus or minus, let's go the square root of 60. Let's do that, and let's put that all over 4. In this case, you would need to simplify the square root of 60, which is, let's see, that's 4 times 15, so that becomes a 2 root 15 all over 4. And now what we see is that there are 1, 2, 3 terms in this expression that all have a common factor of 2, and we would need to divide that out. So dividing everything by a 2 here, this would now become a 4 plus or minus the square root of 15 all over 2. That's as good as that expression would get. But back to the problem we were working on, because you can't do anything with the square root of 61, you are donezo. All right, so there it is. All right, everybody, that is a wrap. That's everything we needed to cover on section 1.2. Let's give that homework problem or homework assignment a try. And if you guys have any issues or questions, you can ask them when we're live in class. You can post them in comments, or you can come see me during office hours. All right, everybody, good luck.